Hello, everybody. Welcome back. Today, we are going to be talking about optimization problems. So, finding the minimum and the maximum in various word problems using area or other things in order to maximize the area or maybe to minimize the perimeter, right? To minimize the amount of material we need. Or when it comes to volume and surface area, perhaps to maximize the volume while minimizing the surface area. Now, why is that useful? Well, perhaps we want to get the most area we possibly can for a set perimeter, right? For a set amount of fence material that we have. Or perhaps we are selling canned soup, right? That's our new business venture. We're selling canned soup, and we would like to know that if we're selling canned soup that are a cup each, what is the best way to make a can, right? What's the best possible way we can make a can while using the least amount of materials? Because the customer is going to pay more if there's more soup in the can, but they're not going to pay more just because we used a whole bunch of material. They don't care how much material we use for the can. And also just in the interest of the environment, using less resources will not only cost us less financially, but will cost us less in terms of the environment. So that's why this is useful. We can maximize an area while minimizing the cost and also the resources extracted from the earth of our material surrounding a fence or something, or we can minimize the cost and production of material when it comes to our soup cans or really any sort of packaging of something that we're selling. So let's talk about how would we do these optimization problems. Well, here are some guidelines. Number one says draw a diagram when possible. And while drawing a diagram isn't mandatory, I do think drawing a diagram does help us to visualize what it is we're trying to maximize, what it is we're trying to minimize, and helps us to complete the problem. So I will be drawing a diagram for every single question we do today. Number two says find the quantity to be maximized or minimized for y. So let's say that it's y, for example. That's the quantity. So it depends. What are they asking? Are they asking us to maximize the area, right? Because then it's the area that is going to be called y, or the area, right, that we're going to distinguish. Or is it the perimeter, right? What is it exactly that we want minimized or maximized? We need to know. Then we need to set up a formula with the variable to be minimized or maximized in terms of just one other variable, because we're not doing multivariable calculus here, we're doing single variable calculus. So it needs to be in terms of just one other variable. If the formula contains one variable other than the quantity that's being maximized or minimized, find other relationships among the variable so that they can be eliminated. That way, our final formula will just contain two variables, which will be y, so quantity to be minimized or maximized, and the other variable. So, in other words, if there are two different variables in our equation other than the area to be minimized or maximized, we need to find other relationships and use substitution in order to get it down to something we can actually differentiate. And then number five says use the algorithm for minimum and max values and check endpoints where possible. So just a reminder, in our last lesson, we talked about how to use that algorithm, right? We did some problems just using that algorithm, which basically that algorithm, just a reminder, consisted of taking the derivative of the quantity that's to be minimized or maximized, and then setting that derivative to zero and solving to find the optimal values. And so that's what they mean by that. And also check endpoints when possible. I think in a lot of these situations, that's not really going to be applicable here necessarily, but where it is applicable, we should also check endpoints as well, as that is a good practice for us to do where possible, for sure. All right, very good. So let's start with this example here. It says an Ennismore farmer has 1,400 meters of fencing and wishes to enclose a rectangular field. One side of the field is against a stream and does not need fencing. The farmer wants to enclose the maximum possible area using all of the fencing. What are the dimensions of the largest possible field? So let's talk about what we want here. Well, we want to maximize the area. And we know that area is equal to base times height, or in this case, I'm just going to say x times y. We also know that one side of the field is against a stream and doesn't need fencing. So I'm going to draw a little picture of the stream, and then I'm going to draw x and y's, right? Now, what's the perimeter of this? Well, the perimeter is going to be 2x plus y. Now, normally the perimeter would be 2x plus 2y. That's a normal perimeter equation. But remember, in this scenario, one of the sides is actually against a stream, and so that one doesn't need fencing. So that's why in this situation, the perimeter is only the three sides and isn't counting the fourth one. Okay? All right, so there we have it. There we have our drawing. Okay, very good. So we know that the perimeter is 1400 meters, right? They told us that the perimeter is 1400 meters, and he wants to use all of it to get the best area that he possibly can, right? That's the whole goal here, is get the best area for the amount of material that he already possesses, so he doesn't have to spend any more money on materials. Okay, very good. All right, so next we need to figure out how to find a prime. Well, before we can find a prime, notice that the area has two variables in it. It has x and y. So what I'm going to do here is I'm going to rearrange this equation to say y is equal to 1400 minus 2x, and then I'm going to sub this in over here and say, therefore, area is actually x times 1400 minus 2x, right? Because 1400 minus 2x is the same as y. And now I'm going to multiply this through and get 1400x minus 2x squared. And now this looks like an equation that is very simple for us to find the derivative of it, right? We know how to do this with just the power rule. So now I'm going to find a prime, so the derivative, which is going to lead us to the maximum, 1 set to 0. So the derivative is going to be 1400 minus 4x. Let's set the derivative to 0 to find the optimal value. 0 is going to be equal to 1400 minus 4x. So 4x is going to equal to 1400. So x is going to equal to 350. All right, so if x is equal to 350, what is y? Well, earlier we said y is equal to 1400 minus 2x, and now we know that x is equal to 350. So that means it's 1400 minus 2 times 350, which is 1400 minus 700, which is 700. So therefore, let's see, what did the question ask? It asked, what are the dimensions of the largest possible field? So therefore, the dimensions of the largest possible field are 350 meters by 700 meters. And we can multiply those two together and get that the largest possible field is 245,000 meters squared if we wanted. And if that's what they asked for, if they asked the maximum area, we would do that. In this case, they actually just asked us what are the dimensions of the largest possible field, so that's why we don't need to actually do that step. But there we have it. We've answered question 1. All right, let's move on to question 2 and question 3. So question 2 says, Chris and Jen are both training for a marathon. Chris's house is located 20 kilometers north of Jen's house. Okay, so I'm going to write that down. Here we have C for Chris's house, and then J for Jen's house. And then this distance here is 20 kilometers. And Chris's house is north. Yeah, okay, cool. So Chris's house is higher, it's north. At 9 a.m. Saturday, Chris leaves the house and jogs south 8 kilometers per hour. Okay, so Chris, he leaves his house and he's going south, so directly towards Jen's house at a rate of 8 kilometers per hour. Then, let's see, at the same time, so also 9 a.m. Saturday morning, Jen leaves her house and jogs 6 kilometers per hour east. Okay, so she's going this way, east, and she's going a bit slower. She's going 6 kilometers per hour east. When are Chris and Jen closest together, given that they both run for 2.5 hours? So basically, that means the value we give can't be more than 2.5 hours because they only run for 2.5 hours and then they decide to stop and decide to take a break and do something else. Okay, so we want to know when they're closest together. So what we want is an optimal value here. We want the minimum value. Something I'm noticing here is that we have something similar to Pythagoras' theorem. We would like to know the minimum distance of this length right here. And that minimum distance, right, this distance can be described as d squared is equal to a squared, which is 6 times whatever time it is, squared, plus 20 minus 8t squared, right? Because this is 20 kilometers and this is 8 kilometers. So it's 20, the distance is 20 kilometers, this length, subtracted from 8 kilometers per however many hours, right? So let's say he's ran for 1 hour, for example, then this number would be 12, right? He has 12 kilometers left before he reaches Jen's house. What if he's only run for half an hour? Well, then he has 16 kilometers left until Jen's house, right? So this distance isn't a fixed distance. This distance changes. And same with this distance, it changes as well. It's 6 times the time, right? 6 times however much time has been elapsed. And that time, of course, cannot be greater than 2.5 hours and cannot be less than 0 because it mentions that they both run for 2.5 hours. So that's how to set up the equation. And I find that it's the setup for most students that's the hardest, and recognizing that this is really just using Pythagoras' theorem and then being a bit more creative as to how we're going to get this distance and this distance exactly, right? Because this distance is relative to whatever time it is. So we don't actually know what the distances are, right? That's what we're trying to figure out in a sense, right? We're trying to optimize that distance. So it's going to be a whole bunch of different distances, but they can all of which can be described by these equations here. So I find for most students who get this question wrong on a test, it's not that they make a mistake while solving for the derivative necessarily, it's the setup of the equation. So understanding how this setup works is 90% of the battle for most people. All right, now let's solve. So d squared is equal to 36t squared plus 400 minus 360t plus 64t squared. That means that d, if we take the square root of both, is going to be 100t squared minus 320t plus 400. And that's all going to be square rooted. And recall that square root is the same as the power of 1/2. The reason I'm writing it this way is because we can then use chain rule when we take the derivative, whereas we don't really have a rule for using the square root directly, which is okay because the square root is the same as power of 1/2. So now let's take d prime. D prime is equal to 1/2 times 100t squared minus 320t plus 400 to the power of negative 1/2, according to chain rule. And also, don't forget that we also have to take the derivative of what's in the brackets. This is the step a lot of people forget. So times 200t minus 320. And there we have it. Now what I'm going to do is I'm going to set this to 0. I'm going to say 0 is equal to all of this. So if we take something to the power of negative 1/2, right, that's the same as putting it on the bottom of our equation. So 100t squared minus 320t plus 400. And let's make our square root sign a bit longer. There we go. And then this 2 is already on the bottom, right? And then the only stuff that's on the top is this 200t minus 320. And that's good because in a second, we're going to just cross multiply up that 2 times root 100t squared minus 322 plus 400, so it doesn't actually matter anymore. 0 equals 200t minus 320, so that means that 200t is equal to 320, which means t is equal to 1.6 hours. Okay, so let's look back at the question because we might actually be done here or we might not be. Let's take a quick look here. It says, when are Chris and Jen closest together? Okay, so it doesn't ask about what position or something like that. It asks when, right? What is the time at which they are closest together? And we've already solved that. We figured out that they are closest together after 1.6 hours. Now, let's say the question didn't ask that, or let's say the question, in addition to that, asked, what is the distance? What is the minimum distance? Well, then what we would do is we would plug 1.6 back into our original distance equation that we made, which was this one up here. Or the simplified version of it is fine too, as long as it's a step before we took the derivative, then we're good. And then we could find it that way. I'm not going to do that because that is not what the question has asked us for. But let's say the question did ask for that, then there would be one more step. And I did want to point that out because sometimes a question might ask that. They might actually ask for what is the shortest distance as opposed to what is the time at which the shortest distance occurs. So just make sure that you're solving the correct question there and you should be good. So therefore, they are closest together after 1.6 hours. And another quick note is that it says they both run for 2.5 hours, and so 1.6 hours is in this equation. It is in this equation. It is part of the interval for which they both run, and so we're good to go. Now, let's say it wasn't. What would we do then? Well, we would look for the endpoints and figure it out that way in that situation, but we did not actually have to do that here because we figured it out without needing any endpoints. Very good. All right, let's move on to example 3. This one's fairly similar, so if the other one was a little bit of a challenge, definitely take let's do this one next. If the other one wasn't a challenge, I actually encourage you to try this one yourself and see if you get it right, and then I will take this one up too. All right, this one says a man is on an island that is 3 kilometers from shore. His favorite burger place is 3 kilometers downshore from the point on the shore closest to the island. The man can paddle his canoe at a speed of 3 kilometers per hour and can run at a speed of 5 kilometers per hour. Determine where on the land on shore. Determine where he should land on shore so that he can reach the burger place in the shortest time. So, what are we optimizing here? Here, we're actually optimizing the time, right? We want to know where he should land so we can have the shortest time. So, we're optimizing time. Okay, so we don't know what time is. They didn't give us an equation for a time, so that means we need to come up with our own. So let's go back to what the question's asking us. It says a man is on an island that is 3 kilometers from shore. So I'm going to put I for our island, and then here is the shore. We'll say S for shore. And this distance is 3 kilometers. Actually, let's make a nicer 3 there. Let's be very clear. That's a little bit better. Okay. And then he can travel from the island at some angle to the shore. And the question is how far, what's this value, right? This is what we're looking at here, is that where should he land on shore, right, relative to the nearest point on shore in order to get to the burger place the fastest. It's also 3 kilometers from here to our burger place. So here's our burger place. Actually, let's do this a bit more to scale. Let's make this make a little bit more sense. There we go. Yeah, if we said that was 3 kilometers, then yeah, let's say that's also about 3 kilometers. And then this is our x, is just from there to there, that part there, of how far relative to shore is he going to go. And then if that's x and then the other one's 3 kilometers, well, 3 kilometers squared plus x squared is equal to x squared plus 3 squared. So that means that the square root of x squared plus 3 squared by the Pythagoras' theorem would be that point there. All right, so now we have actually the information we need to find the time, which is good, or to find not the time, but the equation for the time, which is good, because there's multiple different times that it could take depending what he does. However, we want to know what is the best way to do this, right? What's the best time? What is the shortest time? So time is going to be equal to x squared plus 9, right? Because 3 squared is 9, divided by 3 plus 3 minus x divided by 5. Now, how did I come up with that equation? Well, x squared plus 9 is that oblique distance there, right, is the hypotenuse. And I did divide it by 3 because it says he can paddle his canoe from the island to the shore at a speed of 3 kilometers an hour. So to find the time, we need to divide it, right? Recall that time is equal to distance over velocity, right? Because velocity is distance over time, so therefore time is equal to distance over velocity. And the square root of x squared plus 9 is the distance, and the velocity is 3 kilometers per hour. So that's how we came up with that. And for similar reasons, we can say, well, this remaining distance, oh, here's B for the burger place, this remaining distance here that we still have to go is going to be that full 3 kilometers subtracted from x, right? Subtracted from however much distance he already has based on where he landed on shore, right? So that's where we get 3 minus x from, and then divided by 5 because 5 is our velocity of how fast he can run. That's his running speed. Okay, so now we need to figure out what is x if we are going to maximize that time. So let's do that. Let's do it. Okay, so t prime is going to equal to what? Well, first let's think about this. It's going to be x squared minus 9, or sorry, x squared plus 9 to the negative a half, with a half out here as well, and then times whatever's in the brackets, right? Whatever is in our brackets, which is 2x, and then the 1/3, right? The 3 just kind of stays there. And then for this next part, it's going to be plus, let's see, negative a fifth. Negative a fifth there. And then let's see what we can do. We can actually cancel those out. So we're going to end up with x over 3 root x squared plus 9, subtract 1/5. And we're actually going to set t prime to 0, right? We're trying to optimize this. We're going to set t prime to 0. Okay, so that means what? That means that 1/5 is equal to x over 3 x squared plus 9, right? And then that means if we square both, we're going to get that 25 x squared over 9 is equal to 9 over 9 x squared plus 9, right? So those can cancel out for us. And then we're going to get that we're eventually going to continue with this pattern. We're going to eventually get that x is equal to 9 over 4, or 2.25 if we just continue solving. And let's go back just to see what the question asked. So the question said determine where he should land on shore. So they're asking for what x is, and we figured it out. We said he should land 2.25 kilometers up shore. And there we have it. Awesome. All right, well, that is everything for today. Next day, we'll do 2 problems with optimization regarding economics and science. So we do have an optimization part 2 coming, but that is all for right now. Bye, everyone.